Video is a continuation of photometric image formation R2. In previous video, we have seen the properties of photometric image formation such as lighting, surface condition as well as the optics. We have completed lighting and we are on the surface properties. We have earlier seen about BRDF function, how the BRDF function changed in isotropic surface, and if the light is continuous, we take integral, and if the light is discrete, we take summation. And we are seeing the diffuse reflection. Diffuse reflection probably useful in case of determining the reflection in rough surface, and specular reflection will focus on smooth surface. So we have seen this diagram. The dot product of incident direction and the surface normal is 0 to 1 means the image will be good. If it is negative means the portion won't be captured in a image, right? So previously we know that BRDF can be represented as VI, VR, N cap and lambda. So in this case, if the light is scattered uniformly in all direction, we can say the BRDF is constant. So we can consider 1 for all this term, and we represent FD of lambda. So we are going to determine the reflection. Okay, usually we'll write LR, VR and lambda. Here we are focusing on diffuse, so I'm going to write LD, VR cap and lambda. This represents reflection direction. This represents reflection direction. This represents wavelength, and we know that summation means the light is from the different directions, so we omit Vi. So this is the incident light formula, and we have termed BRDF as constant, so FD of lambda, and there is the foreshortening factor, simplified version of diffuse reflection. So we know this formula. Still we have reduced. We can make BRDF as constant, so we are writing F of lambda, and the same representation is mentioned here. Okay, and cos theta is a foreshortening factor. The cos theta can also be written as the dot product of Vi dot Ni, because we are representing the light on the rough surface as Vi into N factor, N cap, right? Surface normal. So we can replace this cos theta with dot product of incident light vector and surface normal. This plus indicates the value can only be positive, which means it can take all the values greater than 0. The negative values is not possible, because if we take the negative value of cos means the light won't affect the image. So we won't get that image correctly. So if this part, okay, if it is negative means this part won't be captured in a camera. If you are taking a picture from this angle, only this part will be covered, which means cos theta will always be positive. The part which is not covered in the image, we can say the cos theta is negative value. So the cos theta is always positive when the image is captured in a camera. The portion which are not captured in the camera means the cos theta will be negative. So specular reflection, I have already explained this diagram. We are considering a mirrored surface. If the incident light falls in the mirror, it will be reflected in the direction which will be parallel to each other. So we are representing V parallel, and the bottom side is represented as V perpendicular. It is exactly same as of 90 degree. So the total 90 plus 90 would become 180 degree. So we are going to calculate the specular reflection direction. Okay, so we know already the incident direction Vi. The specular reflection direction Si can be calculated as Vi minus twice the value of Vi into N cap. Okay, into again N cap. Okay, so we already know x can be represented as x comma y in the beginning of geometric primitives we have seen, right? So in case of homogeneous representation, we can write in the matrices x and xy. So we can write x as x y transpose. Okay, normal x equal to x comma y can be represented as x transpose of x comma y in matrix form. This we already know. So similarly, on writing this dot product between V I n cap, dot product we know, right? This one we have already explained. V cap into n. This dot product can be replaced with the matrix using the transpose. The normal point can be represented in the matrix using the transpose. So Vi minus 2 into Vi matrix of. Okay, this is not dot product n transpose n cap. By using mathematical property, we can interchange this n cap transpose into Vi. On taking Vi common, we get 2 into n cap transpose into Vi. So we are going to replace the 1 with identity matrix. So 2 into n cap minus transpose into Vi. So this is nothing but Si. Okay, and also we can change this sign Si equal to 2 n cap transpose minus I into V. This Si is nothing but 2 n cap transpose minus I into Vi. Yes, I is calculated from Vi only. So based on this previous image, we have calculated Vi into n cap is changed to a matrix representation. On performing these operations, we are getting Si using this Vi. So this is Si is known as specular reflection direction. Va is incident direction from the view direction, right? Whenever a human view the reflected light, we can say it as Vi. This specular reflection indicates how the light falls off after the reflection. Okay, how the light falls off after reflection. It's not seen by a human. Okay, so that is the Si, which can be calculated by this formula. And we are having two more formulas. One is proposed by Phong, another one is proposed by Torrance and Sparrow. The notation is Fs of theta s and lambda equal to Ks lambda into cos k e into theta s, where k is nothing but exponentiation value. And similarly, Torrance Sparrow stated that same, but with some other different value. Cs is nothing but the inverse of Gaussian width. Okay, so whenever this theta s is large, the image would be more sharper. Okay, so on editing the image, you might have sharpened your images, right? So when the theta s is large, the image will be more sharper. When the theta s is less, or we can say whenever the ke exponentiation factor is large, then we can get a high sharper images. All the edges of our eyes, our mouth in the image will be highlighted. Okay, that is known as sharper images. Okay, then Phong shading. Phong shading is nothing but the combination of both specular and diffuse components. Okay, combination of both specular and diffuse as well as ambient. So ambient plus diffuse plus specular is known as Phong shading. This Ka is a ambient coefficient, Kd is a diffuse coefficient, Ks is a specular coefficient, and La of lambda, it represents ambient light wavelength. And here diffuse we know Li into lambda, Vi into n cap. This we have seen, right? So the same represented here. And in case of specular we have calculated specular reflection direction. So Si is used here. Okay, Br into Si and K power E represents sharpness. The K power E can be only applicable for specular. And this image represents the line plot versus polar plot. Polar plot take angles. Okay, it doesn't take any angles. So the ambient, it is nothing but just a straight line. Diffuse, this represents the cosine curve, and all the exponent value is mentioned here. Okay, this k per e is the exponentiation value. If the exponentiation is 10, we are getting much broader distribution curve. When it is 100, we are getting somewhat narrowed one. When it is 1000, we are getting extremely narrowed down. So if we increase the exponentiation, the sharpness of the image will be increased. The same is represented as angle of 30 degrees, so it is somewhat tilted. Okay, the line plot is same when we perform with the angle of 30 degree. So here also we can get the same narrowed one represents more brightness. Then dichromatic reflection model. Reflection model is a combination of body plus surface components. So assume we are having a table. Okay, assume we are having a table and a light is fixed above the table. So whenever we focus this table, the table, assume this table is in brown color and light is in somewhat yellow with white, yellow plus white color. So whenever we see this table, the brown color will also be shown, and at the top, the light color is also shown. Okay, so that is nothing but if we capture this image, then the light color will also be captured as well as the table color will also be captured. Assume if the light is off, the table will be very dark. Okay, only if the light is available in the night time means we are getting the light color as well as the table color. Okay, so we have dichromatic, it means two, di means two. So it is a combination of both body color as well as the surface color. Okay, so yeah, it is nothing but Li of Br Bin cap, and similarly Lb of Br Bin cap. This Br Bin cap completely represents about the body, sorry, specular, and it completely represents about the diffuse reflection. Okay, so this represents body, this represents surface, and here it can be replaced as Ci and Mi. Ci is nothing but the color of the surface. This Cb represents the color of the light, and M represents the modularity. M represents it. It can be represented in maths as a modular function. Okay, modular function. This lambda is taken with Ci, and the remaining all values should be considered with Mi. Then we are going with optics. Optics is nothing but camera, optics or camera lens. Assume we are going to take an image, okay, either tree or whatever. Consider this as the object and this is the camera. Camera sensor is placed here. Okay, camera sensor is available in this place, and this is the focal length. Okay, if you have a camera means we will have a lens, right? And inside this camera we will have sensor. There will be some distance between sensor to the length. That distance is represented as focal length, f. Okay, and the distance between object to the lens is considered as z naught, and the distance between lens to the camera sensor is known as considered as zi. Okay, this is the very basic diagram representing the optics. So the equation used to represent the optic is 1 by z naught plus zi equal to 1 by f, where f is a focal length. F is called as a focal length of the lens, and z naught is the distance between the object to the lens, and zi is the distance between lens to the camera sensor. Whenever the object is at very long distance, we can't focus. Okay, assume if you want to capture a human who is very far away, then we can't focus. So we are going to take the z naught as infinity, because the z naught is the distance between the object to the lens. So if the object is very far away, we can't capture, so z naught will be at infinity. In such case 1 by infinity, it is nothing but 0. 0 plus 1 by zi equal to 1 by f. On reciprocating it, we get zi equal to f, which is in such case, if the object is very far away, then the image is captured at its focal length. Irrespective of the distance between object to the lens, if the object is very far away, the image is captured at its focal length. And if the focus is not clear, if the focus is not clear, then there will be a blurred image, right? So we know by using a phone, we may take a photograph by focusing some place. If the focus is not clear, sometimes we can get a blurred image, right? So this blurred image represents the circle of confusion. The amount of misfocus is measured by the circle of confusion. If there is misfocus means the image will not be clear. Then the next concept is vignetting. Vignetting is nothing but darkening of an image towards the corners, which means the tendency for the brightness of the image to fall off towards the edge of the image is known as vignetting. There are two types: natural vignetting and mechanical vignetting. Natural vignetting is due to the foreshortening in the object surface. Mechanical vignetting is due to the fault in a periphery of the lens. Natural vignetting means purposefully we are reducing the, or purposefully we are providing some intensities in the edge of the image by changing the theta values. Mechanical vignetting means there is some optical lens, maybe something can be misplaced to get the edge images, darkening of edge images. So that's all about the photometric image formation. As a summary, we have seen three properties: lightning, reflection and shading, and then optics. I hope optics is very clear and it is very simple. Here you may get some confusion. So in order to simplify, let us summarize quickly. BRDF is a four-dimensional function, and we know that it is represented with theta I, theta, psi r. If the image is if the surface is isotropic, we can simplify with psi r minus psi I. It can be further simplified with Vi, Vr and n cap. We have done with surface. Then we are moving with light. If the light is continuous, we are taking integration, and we are going to consider four factors: Li, which is nothing but incident light, and BRDF simplified one, and foreshadowing factor along with D into VA. If it is summation, we won't focus about VA. So these two terms will be omitted. We are taking summation. Next, we are moving to diffuse reflection. In case of diffuse reflection, the BRDF would become a constant. So we are representing only lambda here. The previous equation is further simplified, FD of lambda. In case of specular reflection, we are going to consider specular reflection direction SI, which can be calculated using VI. Using this formula, we have derived this SI like this. Then on combining diffuse as well as specular, we are getting a Phong shading, which is nothing but addition of ambient, diffuse and specular. Ambient, we won't consider any other angle or reflection. So Ka is a ambient coefficient, Kd is a diffuse coefficient, Ks is a specular coefficient, and we are just representing the wavelength. And here diffuse, we are considering the dot product of incident light as well as the surface normal. And in the specular reflection, we are going to consider Si as well as the exponentiation. Whenever the exponentiation is higher, we will get a sharpened images. So on combining all these three, we'll get a better model. Whenever the exponent is high, we get sharper images. That's what represents the previous diagram. Diagrammatic, it is a separate one. If you want to capture both the surface light as well as the body reflection, we can go with the diagrammatic model with this formula. That's it. Thank you.